Okay. Welcome to this NPTEL lectures on robotics, basics and advanced concepts. In this lecture, we will look at mobility of parallel manipulators. So, to introduce this concept of mobility, we can contrast with the concept of workspace in serial manipulators. Okay. All in a serial manipulator, the workspace is defined as all x, y, z and rotation matrices of the end effector such that the real solutions for the inverse kinematics exist. Okay, so basically we gave the position and orientation of the end effector, and then we solve the inverse kinematics, which basically means solve for the joint variables which will lead to that position and orientation of the end effector. If there are real values of the joint variables and the inverse kinematic solution exists, then we say that the given point xyz and the rotation matrix of the end effector are inside the workspace. In parallel manipulator, there are two concepts. First is mobility and the second is workspace. Okay, so remember, the output link is not natural or obvious in a parallel robot, so the workspace depends on the choice of the output link. The mobility, on the other hand, is the range of possible motions of the actuated joint in a parallel manipulator. So we clearly know which are the actuated joints, and as we will see later, that not all possible values of the actuated joints can be achieved. Okay, so in a sense, mobility is more important in parallel manipulators. So the mobility is determined by geometry and linkage dimensions. Okay, or in other words, it is determined by the loop closure constraint equations, which are used to solve the direct kinematics. Okay, mobility is related to the ability to assemble a parallel manipulator at a given configuration. So if I give you values of theta and phi, actuated and passive joint variables, can I assemble the manipulator in that configuration? That is what mobility is related to. So in definition, mobility implies all values of actuated variables such that there are real values of passive joint variables. Okay, and it is determined by direct kinematics. If there are no real values of passive joint variables, the mechanism or the parallel manipulator cannot be assembled at that configuration. Okay, so mobility means obtain conditions for the existence of real solutions for the polynomial in one passive variable obtained after elimination. So remember, in the direct kinematics of parallel robots, we obtained a single polynomial in one of the passive joint variables. And if that polynomial does not give real values, okay, then the manipulator cannot be assembled at that configuration. Okay, and again, as you can remember, elimination was used to obtain that polynomial in one passive joint variable. There are very few parallel manipulators where the direct kinematics can be reduced to the solution of a univariate polynomial of degree 4 or less. Okay, so hence, in most cases, mobility is determined numerically using search. Okay, in a 4-bar mechanism, fortunately, mobility can be obtained in closed form. And again, this is the reason why mobility, a 4-bar mechanism, is used to demonstrate many of the concepts in parallel manipulators and closed loop mechanisms. So the loop closure equation of a 4-bar mechanism was derived in the last lecture. So this equation, eta, theta 1 and phi 1, is basically the Freudenstein equation. Okay, it relates given theta 1, which is the input crank angle, what is the phi 1, which is the output crank angle, in terms of the link lengths L1, L2, L3 and L0. Okay, so on simplification, this eta 1, this equation becomes something like P cos phi 1 plus Q sin phi 1 plus R equal to 0, where P, Q and R are functions of the link lengths and also the angle theta 1. Okay, so you can see cos theta 1 appearing here, sin theta 1 appearing here, and so on. Okay, So if you substitute theta 1, okay, tan theta 1 by 2 as x, and then substitute this tangent half angle substitution. So basically x is tan theta 1 by 2. Then we find out what is cos theta 1 and sin theta 1. Remember, cos theta 1 will be 1 plus x squared divided by 1 so 1 minus x squared divided by 1 plus x squared, and sin theta 1 will be 2x divided by 1 plus x squared. We will get a quadratic equation in x. So this transcendental equation p cos phi plus q sin phi plus r will be converted into a quadratic equation, just like before we have seen many times. And then we can solve for x as a quadratic equation. Okay, we'll have two roots. Okay, and then we can find out the tan inverse of that and multiply by 2, and we will get phi 1. So it turns out that phi 1 is given by 2 tan inverse minus q plus minus square root of p squared plus q squared minus r squared divided by r minus p. Okay, so for real phi 1, p squared plus q squared minus r squared must be greater than or equal to 0. The limiting case when you get two equal real values of phi 1 is when p squared plus q squared minus r squared is equal to 0. So we have two phi's which are coinciding. Okay, in the limiting case, the bounds on theta 1 are cosine theta 1 will be equal to L0 square plus L1 square minus L3 square minus L2 square 2 plus minus L2 L3 divided by 2 L0 L1. Okay, where did I get this from? So we can see here that P, Q, R are functions of sine and cosine theta. Okay. So when this term under the square root of is equal to 0, we can go back and find out what is cosine theta in that limiting case. Okay, and this is what the expression we get. So for full rotatability of theta 1, basically that the 4-bar mechanism can be assembled for any given value of theta 1 in the range 0 to 2 pi. Theta 1 cannot have bounds. Okay, this is the important argument. So if I get a value of theta 1 from this expression, okay, then for that coincident phi, okay, we will get a theta 1 value. Okay, but I want theta 1 to rotate fully and still phi be real. So then we cannot have any bounds on theta 1. So which basically means that there cannot be a solution to this equation. Okay. So let's look at the argument once more. So for real phi 1, we get case condition which is p squared plus q squared minus r squared greater than 0. The two real values will coincide when p squared plus q squared minus r squared is equal to 0. For this limiting case, I can find the value of theta 1, cosine theta 1. Okay. Now, if this theta 1 value were to exist, okay, then we have a phi 1 value where it is coinciding. But we don't want any value of theta 1 because I want the crank to rotate fully. Okay, so theta 1 cannot have any bounds. So there cannot be a solution to this equation. Okay, so basically for full rotatability of theta 1, cosine theta 1 must be greater than 1. So if this number is greater than 1, we cannot have a solution to theta 1, or it should be less than minus 1. Okay. So for full rotatability mobility, to repeat, of theta 1, first phi 1 must be real and then theta 1 be imaginary. Note the order of phi 1 and theta 1. Okay. So the condition C1 greater than 1 and C1 less than minus 1 leads to L0 square, L0 minus L1 whole square greater than L3 minus L2 whole square. So this you can derive from putting C1 greater than 1 here. So you will have some equation which is L0 square plus L1 square greater than or equal to something. Okay. And we also get L0 plus L1 less than L3 plus L2. We can also get two additional conditions from C1 greater than 1 and C1 less than 1, which leads to L3 plus L2 plus L1 less than L0 and L0 plus L1 plus L2 less than L3, these two violate triangle inequality. Triangle equality means the sum of two sides must be greater than the third side for any triangle. Okay. So finally, with this equation 22 gives rise to four inequalities because it's a square. So we can have L0 minus L1 greater than L3 minus L2. Okay. We can also have L1 minus L0 greater than L3 minus L2 if you take the minus sign, and likewise for the other two. Okay. So for the case L1 less than L0, if I assume that the first link, the crank, is less than the base link, we have L0 plus L2 greater than L1 plus L3, and L0 plus L3 greater than L1 plus L2. Okay, remember L0 is the base link, L1 is the crank, L2 is the coupler, and L3 is the output link. So equations 23 and 25 imply that L0, L2 and L3 are all larger than L1. Okay. Equation 23 and 25 also implies in a short form that L plus S less than P plus Q, where S and L are the shortest and the largest link, and P and Q are the intermediate links. Okay, so likewise for L1 greater than L0, the previous one was when L1 is less than L0. Okay, if L1 is greater than L0, we'll have L1 plus L2 greater than L0 plus L3, and L1 plus L3 greater than L0 plus L2. So all these conditions basically coming from the fact that we want the crank, the angle theta1, to rotate fully. Okay, so all of these four conditions in 25, two conditions in 25 and two in 26 can be concisely written as L plus S less than P plus Q. Okay. So if somebody who has done a course in 4-bar mechanisms, analysis or synthesis, we know that this is the Grashof's criteria, which says that the length of the largest and the shortest link should be less than the two intermediate links for the crank to rotate fully, and the crank is adjacent to the fixed link. In the case of a 3 degree of freedom manipulator, okay, we cannot obtain such nice results of when the theta1 or the input actuation can have the full range. In this case, we saw that the polynomial in x3 square was 8th degree. Okay, for values of a 0.5 and L1, L2, L3 between 0.5 and 1.5, we can scan this space and solve the polynomial 8th degree polynomial. Okay, so it turns out that the point marked star, so for example these 2 points here, this point here, this point here, this point here, for L1, L2, L3 in this range, okay, 0.5 to 1.5 in all three actuated variables, there are no real values. So there are no real values for some values of L1, L2, L3. Okay, and hence for these values of L1, L2, L3, we cannot assemble this 3 RPS robot. Okay, so the mobility of this 3 RPS robot, let's go back to the definition. The values of actuated joint variables for which there are real values of the passive joint variables. Okay, and if there are no real passive joint variables, then the mechanism cannot be assembled and the mechanism does not have mobility at those configurations. So it turns out that there are few points where there are no real values of tan theta 3 by 2. Okay, remember this is the numerical technique because we cannot obtain analytical conditions for the 8th degree polynomial. When is the 8th degree polynomial giving real values? So like any numerical technique or any numerical search, if you refine the region, if you take smaller and smaller steps, the mobility region may look different. Nevertheless, this is the way to determine the mobility of this 3 RPS manipulator. So in summary, the mobility in parallel robots is analogous to the workspace in serial manipulator. Okay, the actuated joints can be restricted, okay, and not due to joint limits. This is important. So given a range of actuated joint, if I do not have real values of the passive joint variables, I cannot achieve those actuated joint variables. And this has nothing to do with the joint limits, which are there in serial robots. So the mobility of actuated joint determines if a parallel manipulator or a mechanism can be assembled in a configuration. Okay. So if I tell you the passive and active joint variables, I can assemble the parallel manipulator. But if there are no real passive joint variables, we cannot assemble the parallel robot. Okay. So just to repeat, if no real solutions to the direct kinematics problem, it is not possible to assemble the parallel robot. Analytical solutions for mobility of a 4-bar mechanism yields the well-known Grashof's criteria, L plus S less than P plus Q for theta 1 to be fully rotatable. Okay, so there is no problem of assemblability in a 4-bar mechanism when the crank rotates fully. It is difficult to find mobility analytically for other parallel manipulators and mechanisms, simply because the direct kinematics problem cannot be solved in closed form. Okay, and hence for such parallel robots we have to do basically numerical search. Okay, we scan the actuated joint variable space and find out where the passive joints are imaginary. So with this we'll stop. Okay, clearly this is a big topic. Lots of research has been done for different kinds of parallel robots for its mobility, but these are the ones which can be done quite easily, or at least discussed quite easily. In the next lecture, we'll look at inverse kinematics of parallel robots.